Welcome to Lesson 7.4, Applications of Linear Systems. So in Lessons 7.1 through 7.3, we looked at three different methods for solving linear systems. One method was graphing, one was substitution, and one was elimination or combination. So now in this lesson, we are going to look at the idea of when each method should be used. So when choosing the best method, we can kind of summarize it to these little hash marks below each method. So for example, you'd want to choose graphing when both equations are already in the y equals mx plus b slope intercept form. So if both equations are already in y equals mx plus b, graphing would be the best method. For substitution, if one variable is alone, or if one variable has a coefficient of 1, meaning the number in front of it is just 1, like 1x or 1y. And then for elimination, we'd want to use elimination when the terms are already lined up vertically. So x over x, y over y, constant over constant. We have opposite coefficients already, or all the variables have coefficients that are different than 1. So if any of those three are the case, then we'd want to use elimination or combination. So when you're deciding what's the best method, you want to look at the hash marks below each of these options. So let's look at a few examples. Example 1a says choose the best method for solving and explain the reasoning, then solve using that method. So in A, I have 3x minus y equals 3 and y equals x plus 3. So in this case, y is already alone in my bottom equation. So if one variable is already alone, I'd want to use substitution. So then I'm going to use substitution by putting the x plus 3 in place of y in the top equation. So 3x minus y equals 3 would become 3x minus, in parentheses, x plus 3 equals 3. So we need to distribute this minus or subtraction sign. So it would become 3x minus x minus 3 equals 3. Combine our x's. 3x minus 1x is 2x. So 2x minus 3 equals 3. Add 3 to each side. And then we have 2x equals 6. Divide by 2. And x equals 3. Now that I know x equals 3, I'll substitute that back into the second equation, y equals x plus 3. So y equals x plus 3, replace the x with 3. So y equals 3 plus 3, or y equals 6. So our solution would be 3, 6. In part B, we have two equations, y equals 1/2 x minus 4 and y equals a negative 2x plus 1. Both of our equations are already in y equals mx plus b, slope-intercept form, so we would use graphing. So we want to graph both lines first. So I just cut out some graph paper. Feel free to draw your own graph for your notes if need be. And the top equation, y equals 1/2 x minus 4. I know my y-intercept is at a negative 4. So starting at 0, 0, go down to a negative 4, put our point. And our slope is 1/2, meaning up 1, right 2. Up 1, right 2. So you can see the gold line here is y equals 1/2 x minus 4. Then for the bottom equation, y equals negative 2x plus 1, y-intercept is a positive 1. So from 0, 0, go up 1. And our slope is a negative 2, so down 2, right 1. Down 2, right 1. We can see that the two lines intersect at the point 2, negative 3. So what you want to do is check that 2, -3 by plugging it into each original equation. So put the 2 in for x, -3 for y. So in that top equation, when we substitute in the 2, -3, we'd end up with -3 equals 1/2 times 2 minus 4. Or -3 equals 1 minus 4. -3 equals -3. So yes, that's a solution to the first equation. Check it with the second. Y equals -2x plus 1. Put in the -3 for y and the 2 for x. And we end up with -3 equals -4 plus 1. -4 plus 1 is -3. So that solution works for both equations. So we know our final solution is 2, -3. And then let's look at C. In C, we have 2x plus 3y equals 3, 5x plus 5y equals 10. Well, my terms are already lined up. Each term has different coefficients. So in this case, terms are lined up. Each one has different coefficients. We want to use elimination. So we need to decide, are we going to cancel the x or the y? I'm going to cancel the x's. So the top equation, I'm going to multiply by -5. Bottom equation, multiply by 2. So I end up with, on top, -10x minus 15y equals -15. And on bottom, 10x plus 10y equals 20. Now, the -10 and positive 10x are opposites, so they'll cancel when I add my two equations. And we end up with a -5y equals 5. Divide by the -5, and y equals -1. Now I'm going to take that and substitute it back into one of my original equations. So I put it back into 2x plus 3y equals 3. So 2x plus 3 times -1 equals 3. 2x minus 3 equals 3. Add the 3 to each side. Divide by 2. And x equals 3. So we know our solution to this system is 3, -1. So again, when choosing which method to use, you want to look at the rules up here. Now on the back side of our notes, we have some word scenarios that first we want to write as a system of equations, and then we want to use the best method to solve. So in the first one, example A here, we're dealing with a baseball game, hot dogs, and sodas. So it doesn't matter if you would make the hot dogs x and the sodas y, or flip it, as long as you did the same in both equations. But in my case, I'm going to make hot dogs my variable x, soda my variable y. So as I read through the word scenario, it says one person buys 5 hot dogs and 3 sodas. So that tells me it'd be 5x plus 3y for $15.50. So I have my first equation. 5x plus 3y equals 15.5 right here. Then for the second equation, another person bought 2 hot dogs and 2 sodas, so 2x and 2y, for $7. So 2x plus 2y equals 7. Now I have my two equations. 5x plus 3y equals 15.5, 2x plus 2y equals 7. In this case, my terms are lined up. I have different coefficients, so I want to use elimination or combination. So I decided to cancel the x's. So I'm multiplying my top equation by 2 and the bottom equation by -5. So when I do the multiplication, I end up with 10x plus 6y equals 31 for the top equation, and -10x minus 10y equals -35 for the bottom. Add the two equations, our x's cancel. 6y plus -10y is a -4y. 31 plus a -35 is a -4. So -4y equals -4. Divide both sides by the -4, and y equals 1. Now I can take that y equals 1 and substitute it back into either of my original equations. So I put it into the 2x plus 2y equals 7. So 2x plus 2 equals 7. Subtract our 2, 2x equals 5, divide by 2, and x equals 2.5. So now when we're answering the final question, how much does each item cost? Hot dogs were the letter X, so taking 2.5 and writing it as money would be hot dogs cost $2.50. Soda, the letter Y, cost $1 each. So now letter B, or example B. Health food store mixes granola and raisins to make 20 pounds of raisin granola. Granola costs $4 per pound and raisins cost $5 per pound. How many pounds of each should be included if they want the mixture to cost $85? So the first equation comes from the fact that we're mixing granola and raisins to make 20 pounds. So if granola is X and raisins are Y, X plus Y equals 20. First equation. Second equation, granola being $4 per pound, we'd represent that by 4x, and raisins being $5 per pound plus 5y equaled the $85 total. So 4x plus 5y equals the 85. So what I notice is one of my variables on top, well actually both, x and y have coefficients of 1. 1x, 1y. So I'm going to use substitution. So what I need to do first on that top one is to solve it for x or y. I solved it for x. So x would equal 20 minus y. Now we're going to substitute in the 20 minus y for x in the other equation. So we'd have 4 times 20 minus y in parentheses plus 5y equals 85. Distribute the 4. 80 minus 4y plus 5y equals 85. Combine our y's on the left. Negative 4y and positive 5y is just 1y. So we have 80 plus y equals 85. Subtract the 80, and y would equal 5. So now we know the value of y, and we can substitute that back into one of the original equations, the one that we did not solve yet, meaning the top one, to figure out what x is. So if x plus y is 20, and we know y equals 5, x plus 5 equals 20, subtract 5, and x equals 15. So in this case, we would use 15 pounds of granola and 5 pounds of raisins. That means the mixture would cost 85 pounds and weigh 20 pounds total. And now in part C, we're offered 2 different jobs. Job A gives you a $30,000 salary plus 1% sales bonus. Job B is a $24,000 salary plus 2% sales bonus. How much would you have to sell to make the same amount in each job? So in this case, job A, if we wrote that as an equation, it would be y equals 1% as a fraction, meaning 1 over 100x, plus $30,000 for our base salary. So the 1% bonus is our fraction for our slope. For job B, the 2% would be represented as 2 over 100x, plus the $24,000 base salary. So when we write these equations out, both equations are in y equals mx plus b. So graphing would work. The only problem is our graph would be quite large, unless you change the scale, but still it's going to be a rather large graph. So what we can do in this case, and we'll look at these a little bit more in our next lesson about special types of systems, but we can just simply put job A equation or expression equal to job B. And then we can solve that for x. So I'm actually going to use substitution because I know y equals 100 or 1/100th x plus 30,000 and y equals 2/100th x plus 24,000. So I just set those two equal to each other. Then I want to solve for whichever one you want, but we're solving for x in this case, so y would equal. So the y's cancel and we set them equal, we need to solve for x. So 1/100th x plus 30,000 equals 2 over 100x plus 24,000. Subtract the 1/100th x from each side, and we have 30,000 equals 1 over 100x plus 24,000. Subtract the 24,000 from each side, and we have 6,000 equals 1 over 100x. So to get x alone, instead of multiplying by 1 over 100, we're dividing each side by 1 over 100. That means x would equal 600,000. So they would need to sell $600,000 worth of whatever it is that they're selling at this job for the two jobs to be equal. So in this case, even though both were y equals mx plus b, graphing would be an option, but because the graphs are so large, we want to set them equal by substituting for the y. So we can take the 2 over 100x plus 24,000 and put it in for y in the first equation. So this time we're going back to our initial rules, and even though the graphing could work, it didn't make sense to do the graphs because of the size. So then we would go to substitution because one of the variables has a coefficient of 1 and the variable's already alone. So sometimes if it doesn't make sense to use one of the approaches, like the graph would be so large, you may want to check if you could use substitution in its place.